Hi guys, welcome back to our physical chemistry lecture series. So today we'll be discussing real gases. So previously we were talking about the gas laws that describes the behavior of the ideal gas, and we also talked about the kinetic molecular theory, which explains this behavior on a molecular basis. So today let's look at the limitations of the kinetic molecular theory and the ideal gas description when it comes to describing real gases. So an ideal gas obeys PV is equal to nRT at all pressures and temperatures. So the kinetic molecular theory gives us a molecular basis as to why the ideal gas behaves this way. Okay, so according to KMT, for an ideal gas, the gas molecules are infinitely small to the extent that we could neglect the molecular volume of the gas. Okay, so we're just going to be treating the gas molecules as point particles. So KMT also says something about the intermolecular forces of attraction in gas, so namely that they don't have any interactions with one another. Okay, so however, we know that for real gases, okay, so gas molecules in a real gas, they really do have volume, okay, and they also exert attractive forces on each other, okay? So we can't treat all gases as an ideal gas at all conditions because there does come a point where the intermolecular force of attractions as well as the size of the gas molecules become significant enough to influence its behavior. So a notable case for this is when we have conditions in which the intermolecular forces of attraction cause the gas to start liquefying. Okay, so this is the part where we have to start considering intermolecular force of attraction because we have phase changes. So for an ideal gas will remain a gas in all possible conditions. But real gases, we know that they could start liquefying and even solidifying based on the conditions in which the gas is in. All right, so let's consider Boyle's law. So we could start seeing the deviation of an ideal gas from a real gas by looking at the ideal gas isotherms. Okay, so recall again that Boyle's law tells us the relationship between pressure and volume for an ideal gas at constant temperature and number of moles. Overall, we know that there's an inverse relationship, so we could draw isotherms. Okay, so over here we see this curve over here which describes the behavior at temperature 1, and even if we start decreasing the temperature to temperature 2, temperature 3, temperature 4, we still see the same relationship between pressure and volume. So we see these nice smooth curves. However, once we start looking at real gas isotherms, this is when we start seeing some deviations. Okay, so for temperature 1, we still see this nice PV curve. However, if we start decreasing the temperature enough to say temperature 2, okay, we start to see some really strange shapes in our typical smooth curve over here. Okay, so if we even decrease the temperature even further, this is when we start seeing these strange discontinuities in our plots. Okay, so let's look at another temperature. So there we go, we still have these discontinuities. Okay, so keep in mind that if we start decreasing the temperature, so say that you have a case of a container of water vapor, what happens when you start decreasing the temperature? So if you start decreasing the temperature, what tends to happen to all that water vapor is that it starts to condense. Okay, so the kinetic energy of our gas is not enough to escape the intermolecular force of attraction that causes the condensation of our gas to a liquid. So this is when we start seeing it. So actually, in particular parts of this curve, we have a liquid and we have our vapor part over here. So in between, this is when we start seeing our phase changes. So we'll have a more lengthy discussion on this plot a little later. But overall, just keep in mind that we have to consider, for one, the intermolecular forces of attraction between our gas molecules. Okay, so let's look at the two types of intermolecular force of attraction that can occur, namely attractive or repulsive forces. Okay, so we'll be using this model. So we have HCl, or hydrogen chloride gas. Okay, so hydrogen chloride, is a polar molecule. So we have a partial positive charge over here and a partial negative charge over here. So we expect that HCl is going to have dipole-dipole interactions. So that's an attractive force. So at this point, however, these two HCl molecules are pretty far apart from one another. Okay, so let's say that at these particular conditions, this distance r is pretty much approaching infinity. So this occurs when we have really low pressures and high temperatures. So why do we need to have really low pressures? Okay, so recall again that for gases, pressure is inversely proportional to our volume. So if we have really low pressures, we have very, very large volumes, okay? So if we have very, very large volumes, this implies that the distance between our two molecules is very, very large, or pretty much infinity. Okay, so these particles are super, super far from one another, and also the temperature is very high. So there's not really a chance for them to approach one another so that the dipoles will take hold of one another. Okay, so pretty much the dipole-dipole interactions that these two molecules could potentially have is negligible. Okay, so the temperature is very high, so if ever they do approach one another, their kinetic energy could pretty much overcome the intermolecular forces of attraction that could hold them together. So what happens, however, when we bring these two molecules a little bit closer to one another? Okay, so let's say that we have a moderate distance between these two molecules. So this usually occurs at moderate pressures. Okay, so at this point, we now have a small enough space between these two molecules so that they could have our attractive interaction. Okay, so the partial negative charge of this molecule is close enough to the partial positive charge of this molecule so that they could have their dipole-dipole interaction. Okay, so when these two molecules approach one another, they're going to be drawn even closer to one another. Okay, so let's keep that in mind. However, if we force them a little bit too close to one another, this is when they start repelling each other. Okay, so this usually occurs at very high pressures. Okay, so imagine you have a container with a gas and then you increase the pressure. You're pretty much drawing all of your molecules closer together. You're forcing them to come into contact with one another. And this distance is unfavorable now because we have to keep in mind that molecules, they're made up of positive nuclei and they're also made up of negatively charged electron clouds. So if they become way too close to one another, they start to repel each other. Okay, so the electron clouds, negatively charged, if they start forcing their way into their personal space, they start repelling each other. Okay, so if we force our molecules to become this close, okay, they're going to want to push away from one another. All right, so again, let's just keep that in mind. So let's summarize the two types of attractions. Okay, so if we have a moderate distance between our molecules, attractions are going to dominate. Okay, so if we have these two molecules together, they're going to be drawn even closer to one another. If repulsions are dominant, so this occurs at very high pressures, they're too close to one another, so they don't want to be this too close, or they're going to want to push away from one another. So overall, if attractions are dominant, okay, the molecules are going to be pushed closer together, and if repulsions are dominant, they're going to be pushed farther apart. So in terms of compressibility, okay, so if attractions are dominant, the gas becomes more compressible. Okay, so it's going to be easier to decrease the volume of our gas because the intermolecular forces of attraction are assisting you in decreasing the volume. Okay, so our gas is more compressible. However, if we try to push our molecules too close together, if we try to compress them too much, okay, it's going to be harder to do so because we have some repulsive forces that are going to prevent you from pushing your molecules even closer together. All right, so overall, we could say something about the real gas volume versus the ideal gas volume. Okay, so if attractions are dominant, you expect that since our gas is more compressible, the real gas volume is going to be smaller than the ideal gas volume. Okay, so keep in mind that an ideal gas volume is when our molecules have no attractions whatsoever. All right, so if we have repulsions dominant, however, okay, so keep in mind that our molecules want to get further apart from one another, the real gas volume is expected to be larger than the ideal gas volume. All right, so we could make use of this different compressibility of our gas based on different conditions. Keep in mind that attractions tend to dominate at moderate pressures and low temperatures, whereas repulsions dominate at high pressures. So we could summarize these different changes using our so-called compression factor or compressibility factor, Z. So Z pretty much just tells us a ratio of the real gas volume, molar volume in particular, and the ideal gas volume, right? So overall, if Z is less than 1, okay, so if Z is less than 1, this implies that Vm real is less than Vm ideal. Okay, so this implies again, so recall again what type of attractions are dominating. This implies that attractive forces are dominant. Okay, so the gas is more compressible. So when Z is greater than 1, this implies that the real gas volume is greater than that predicted by the ideal gas equation. Okay. So since the real gas volume is larger, okay, it becomes less compressible, therefore repulsions dominate. Okay, so of course when Z is equal to 1, okay, this implies that our real gas volume is equal to our ideal gas volume. Okay, so we'll see which conditions this could occur. All right. So we could also express our compression factor in another way. Okay, so let's just use our ideal gas equation. So we do have an expression for the molar volume of an ideal gas after all. So for example, let's write this down, Vm ideal. Okay, so this is the volume of 1 mole of gas. So we know from the ideal gas equation that volume is equal to RT over P. Right? So we could just replace this term over here with this expression. Okay, so Z becomes Vm real. So this is a thing that you're going to be measuring. And these are the conditions that you're going to have. Okay, so replace Vm ideal with RT over P. RT over P. So just a little bit of rearrangement. Let's bring this pressure up over here. So Z becomes PVM, okay, molar volume of our real gas, which we can measure, divided by RT. All right, so this is just another way of expressing our compressibility factor. So let's look at the variation of Z of a certain gas at varying temperatures. So here we have a plot of compression factor versus pressure. Okay, so we have different temperatures here. We have a low temperature, moderate temperature, and a high temperature. All right, so over here we have a value of 1, so this corresponds to that of a perfect gas or an ideal gas. So note that regardless of the conditions, regardless of the pressure, regardless of the temperature, the perfect gas is always going to have a compression factor of just 1. However, for real gases, okay, so it's going to vary based on the temperature. Okay, so let's look at this plot over here. So this is our marker here of our value of 1. So if Z is greater than 1, so this corresponds to this part of the plot here, Z greater than 1. Okay, so what do we know about the forces of attraction that are dominant here? If Z is greater than 1, our real volume is going to be greater than the ideal volume, so our gas is less compressible. So this implies that repulsive forces dominate. Okay, so when Z is less than 1, however, this is when our attractive forces dominate. Okay, so what did we mention again about which attractions would dominate at which conditions? Okay, so we did mention something about attractive forces dominating at moderate pressures. Okay, so moderate pressures meaning that we're just pushing the molecules close enough so that the intermolecular forces of attraction could take hold. So let's look at this particular curve over here at low temperature, right? So we see that at moderate pressure, so just around over here, this is at this particular isotherm, this is our moderate pressure. Okay, So this is when Z is less than 1. So attractive forces are dominating. Okay, so note that it's at low temperature. Okay, so low temperature, so the kinetic energy of our molecules is low enough so that intermolecular forces of attraction can take hold. However, we also said something about when repulsive forces are going to dominate. Okay, so repulsive forces are going to dominate at high pressure. So for this particular isotherm, at this particular temperature, if we increase the pressure high enough, so at this point here, okay, so this is like our limiting pressure. At pressure is greater than this here, we start seeing our Z become greater than 1. Okay, so this means that we pushed our gas molecules way too close to one another so that repulsive forces are starting to dominate. All right? Okay, so at this particular isotherm, however, we don't really see this dip in our curve anymore. So at all pressures, we have repulsive forces. All right, so at this particular temperature, we could say that the kinetic energy of our molecules are so high that they always overcome the attractive forces in our gas. Okay, so attractive forces cannot take hold, therefore we always have our repulsive forces dominating at all pressures. Right? So note, however, that at all temperatures, our low temperatures, our moderate temperature, and our high temperature, that at a zero pressure, okay, so this is when pressure approaches 0, they all start at the same point, at the same value of Z. So as pressure approaches 0, our Z value always approaches 1. Okay, so what does this imply? When we have a 0 pressure, okay, so this is our very, very low pressures that is consistent for our ideal gas behavior. Okay, so when we have very, very low pressures, okay, this is when our molar volume approaches infinity. So that means we have infinite distances between our gas molecules. Okay, so if we have infinite distance between our gas molecules, they pretty much have no intermolecular forces of attraction towards one another, or they pretty much become negligible. So they start behaving as an ideal gas here. Right, so this is the thing to keep in mind. So another thing to keep in mind as well is the dip with this curve over here. Okay, so we did mention that at higher temperatures, the kinetic energy of our gas is so high that it overcomes all intermolecular forces of attraction. So if we start decreasing the temperature low enough, so we always start seeing this this dip over here. Okay, so this is at an even lower temperature. Okay, so the greater the dip, the smaller our compression factor Z becomes. Okay, so this is when we have greater intermolecular forces of attraction holding our molecules together. So we could decrease the temperature enough to the extent that we start to have condensation. Okay, so the temperature is so low that the kinetic energy of our gases is low enough to cause condensation or liquefaction. Okay, so overall, lower temperature, we tend to have lower dips here. Okay, so this implies that the volume of our real gas is much, much lower than the volume of our ideal gas. Okay, so this happens to the extent that the volume of the real gas starts approaching that of a liquid. Okay, and we do know that the volumes of liquids are much, much smaller than the volumes of gases. Right, so overall, we could start seeing that intermolecular forces of attraction are taking hold in order to have liquefaction or condensation, phase changes. All right. So there's also another temperature here of interest. Okay, so this is the moderate temperature between the low temperature and the high temperature isotherms here. So what's interesting about this is this part over here. All right, you see this? Okay, so let's zoom in a bit. Okay, so we see here that for this temperature, we have a really, really close behavior of our real gas to that of the ideal gas. So in other words, for an appreciable pressure, the Z value of our real gas is 1. Okay, so this temperature here, this corresponds to the so-called boil temperature. So overall, this is defined as the temperature at which a gas follows the ideal gas law at an appreciable pressure range. Okay, so note that for other temperatures, we tend to have deviation immediately after a pressure of 0. For this, however, we kind of have a more tangential curve over here. So for an appreciable pressure range, we have the ideal gas law followed, right? So this is a really nice temperature to take note of. So this is going to be unique for every gas. All right, so keep in mind that this plot over here, this is just for a certain gas at varying temperatures. So we could also start looking at the plot of Z versus P for different gases. All right, so here we have different types of gases at a constant temperature. So this is when we start having different curves based on different temperatures. So this is expected since we have these different gases that have different strengths of intermolecular forces of attraction. Okay, so at this particular temperature, we can see that H2 gas, hydrogen gas, it's always going to be greater than 1. Okay, so repulsive forces are always going to be dominant here. Okay, so actually we could explain the shapes of these curves based on what we know about the intermolecular forces of attraction of these particular gases. So for example, we see that we have a very low Z value for ammonia. Okay, so recall again, the greater the dip here of our curves, the greater the intermolecular forces of attraction that are taking hold at these conditions. Okay, so for NH3, we know that this has hydrogen bonding. All right, so this is a very strong intermolecular force of attraction. Okay, so what about this? This is ethylene. Okay, so we could have some van der Waals forces. Okay, so we also have van der Waals forces for our methane and for our hydrogen gas. But we know that van der Waals interactions or London dispersion forces tend to be stronger for larger molecules. So this also has a stronger intermolecular force of attraction compared to hydrogen gas. All right. So we could kind of compare the different intermolecular forces of attraction based on the shape of their Z curves, okay? So again, for all types of gases at pressure approaching 0, for all gases, our Z approaches 1, okay? So overall, the behavior of all gases at a 0 pressure is always going to approach that of an ideal gas. All right, so that's why we call the ideal gas equation of state a so-called limiting law. Okay, so at the extreme cases, at a pressure approaching 0, or we could also look at this as a molar volume approaching infinity. Okay, so all gases at all temperatures, okay, it always approaches ideal gas behavior. Okay, so when we start constructing real gas equations of state, we should always have this condition here. Okay, so at the limiting conditions, 0 pressure, infinite molar volume, okay, our equation of state should always reduce to the ideal gas equation of state. Okay, so we'll be seeing that later on with the different equations of state that we'll be constructing. So based on this, actually, on the different values of Z, we could also construct our equation of state from here. Okay, so we could see here that for different gases, we have different curves. Okay, and then these compression factor versus pressure curves could also tell us something about the behavior of gases at different conditions, right? So we could use this data here in order to construct an equation of state. Okay, so how did we get these curves, by the way? Okay, so all these curves here were determined experimentally. So the volume of these different gases were measured at different conditions, and the compression factor was calculated at these different pressures. So we were able to construct these curves. Okay, so these lines here are actually extrapolations of experimental data. So one way that we could look at this as well is if you're plotting some data, say for example, you're plotting y and then x, okay, so we have all your data over here, okay, so what we're doing here is that we're just connecting these points, we're drawing a line here. So we're doing linear regression. So linear regression is also another form of so-called curve fitting. Okay, so you're making extrapolations and interpolations based on your available data. So based on this, based on our linear regression, we end up with an equation, right? So based on this, we can have y is equal to mx plus b. Okay, so based on different types of behavior, okay, so we're going to have different values of m and b, right? So for this curve example, for example, we have y is equal to mx plus b. For this curve, we have y is equal to, say, m2x plus b2, okay? So each curve is going to have their own unique constants here in order to describe their behavior on this curve. Okay, so note again that each gas, they're going to have variable behavior. So the equation of state that we're going to be constructing is going to have specific terms for each type of gas. So our general equation for curve fitting can be given as follows. Okay, Z is equal to 1 plus B prime P plus C prime P2 onwards and onwards. So we use this general form of our equation and we just specify the constants based on the shape of the curve that we get over here. Okay, so these coefficients, the B prime and the C prime, these are called your virial coefficients. Okay, so this equation can also be written in terms of molar volume. Okay, so instead of B prime we have B, instead of C prime we have C. Okay, so keep in mind that these are going to be different constants since we have our Z in terms of another equation. Okay, so our B over here, this is called our second virial coefficient. Okay, so B prime, our second virial coefficient, can either be positive or negative. Okay, so this constant here tells us something about the behavior of the Z curve at moderate pressures. Okay, so if B is positive, okay, so this is when repulsions dominate. Okay, so if B is positive, we will have a curve very similar to hydrogen gas over here. Okay, so we have an upward shaped curve here without any dip. However, if we have a negative value for B, our second virial coefficient, this is when we start having attractive forces that could dominate at these conditions. Okay, so negative values suggest that we have a negative sloping part of our curve. So for these particular curves here with a dip here, we expect that their second virial coefficients are going to be negative. All right, so the other virial coefficients, so C over here, this is called your third virial coefficient. Okay, so this actually continues on. You could have D prime P raised to 3, etc., etc. Okay, so these are always going to be positive. Okay, so same thing goes over here. So B here, this is the second virial coefficient. C, this is our third, etc., etc. Okay, so B could also be positive or negative, and this implies something about the intermolecular forces of attraction at these conditions. Okay, and C onwards is always going to be positive. All right, so also note, guys, that recall again that these curves are going to be different for each temperature. So our virial coefficients, these are also going to be different based on temperature. Okay, so these vary based on temperature and of course what type of gas we're talking about. Okay, so how can we construct an equation of state from our expressions for Z? Okay, so let's start with this expression over here. Okay, so we know something about the expression of Z, right? So we mentioned something about this before earlier. Okay, so Z, we define this as the ratio of our real gas volume over our ideal gas volume, and we can also write this in terms of Vm. Okay, so this is for real gas volume over RT. Okay, so if we rewrite this, we have PVM is equal to Z RT. Okay, so let's just replace Z with the expanded expression over here. Okay, so PVM is equal to RT times 1 plus B prime P plus C prime P squared onwards. Okay, so this is our virial equation of state. Okay, so let's also write another equation of state in terms of this here. So same treatment, we could write our expression for Z in terms of PVM is equal to ZRT and replace Z with this expression here. So we have PVM is equal to RT times 1 plus B over VM plus C over VM squared onwards. Okay, so this is another form of our virial equation of state. Okay, so we also said something about how all real gas equations of state should reduce to the ideal gas equation of state at the limiting conditions, namely low pressures when pressure approaches 0 and when molar volume approaches infinity. Okay, so let's check out the behavior of this as P approaches 0. So when P approaches 0, these additional terms over here, so these are like corrective terms for the ideal gas equation of state. So when P approaches 0, this term approaches 0, this term also approaches 0, and ultimately our equation reduces to the ideal gas equation of state. Okay? So since this is molar volume is, recall, just volume over number of moles. You could also write this as PV is equal to nRT, our ideal gas equation of state. So the same treatment can go over here when the molar volume approaches infinity, as is with the case for an ideal gas. Okay, so when an infinity term is in a denominator, this term approaches 0, this term approaches 0 as well. So this equation here, our virial equation of state, pretty much just approaches the ideal gas equation. Okay, so we could write this again as PV is equal to nRT. Alright? Okay, so this is our first real gas equation of state derived from experimental data. Okay, so our experimental data was from our compression factor versus pressure curves at different temperatures. Okay, so we have all these additional constants, our virial coefficients, to account for the variable behavior of our different types of gases. But keep in mind again that the virial equation of state is empirically derived. So we don't really get any insight on the molecular behavior of our gas. Okay, so it doesn't really tell us anything else in terms of the molecular volume of our gas or intermolecular force of attraction. Okay, so equations of state have to be derived experimentally. Okay, so we have the van der Waals equation of state that gives us more of a model to explain the different behavior of real gases versus ideal gases. Okay, so this was proposed by Johannes van der Waals in the 19th century, and he considered the different assumptions of the kinetic molecular theory that limits the ideal gas equation. Okay, so namely that gases, the gas molecules themselves, have no volume, and then gas molecules do not interact. So what van der Waals did was that he added corrective terms to take into account these factors that would influence the behavior of our gas. So what van der Waals did was that he added corrective terms to the ideal gas equation of state. Okay, so let's write down the ideal gas equation. So P ideal, okay, so the pressure predicted by the ideal gas equation times the volume of an ideal gas is equal to nRT. Okay, so what we're going to do here is that we're going to add corrective terms to our pressure term and our volume term. Okay, so pressure is going to be affected by the interactions of the molecules with one another, and our volume term is also going to be affected by the volume of the actual gas molecules. Okay, so what we're going to have here is that we're going to be including corrective terms. Okay, so actually the ideal pressure is going to be equal to the real pressure plus some corrective term, so P prime. The volume, the ideal volume, is going to be equal to the real volume plus some corrective term, right? So P ideal, this is going to be equal to the real observed pressure plus some corrective term times the real volume plus some corrective term. This is going to be equal to nRT, right? So this is going to be our basis for the van der Waals equation of state. So we just need to figure out what these corrective terms are going to be. Okay, so let's look first at the volume correction. Okay, so let's consider again an ideal gas. Okay, so an ideal gas is going to have the ideal volume. Okay, so we pictured our ideal gas as just point particles, right? So the actual gas molecules do not occupy space. Okay, however, once we start looking at a real gas, okay, the gas molecules do occupy a significant amount of space. Okay, so keep in mind that since our gas molecules actually do occupy some space, the real gas volume is going to be larger than the ideal gas volume. Okay, so in particular, this is actually the volume occupied by our real gas. Okay, so the volume of the real gas is expected to be greater than the volume of the ideal gas. Okay, so we could visualize this by separating the volume of our gas molecules. So we could represent the volume of our real gas in the following way. So we have the ideal gas volume represented by this blue part over here, and the volume of our gas molecules represented here. So overall, this entire part here, the blue part and the red part, this is the real volume of our gas. So this is composed of our ideal gas volume as well as the volume of our real gas, which is represented by this term over here. So this is our corrective term, NB. So NB, okay, so this is the part that we'll be adding. So this is the van der Waals volume correction. Okay, so this takes into account the so-called excluded volume of the gas molecules. Okay, so B is our van der Waals constant. So this is unique for each gas and it's related to the size of our gas molecules. So this is in terms of volume of the gas molecules per mole. So B is in terms of liters per mole. So if we're going to write this down, so the volume of our real gas is equal to the volume of the ideal gas plus the corrective term over here. Okay, so this takes into account the so-called excluded volume. So let's try to include this term in our corrected van der Waals equation. All right, so our expression again is V real is equal to V ideal plus the volume of our gas molecules. Okay, so recall again that our equation was P ideal times volume ideal is equal to nRT. Okay, so we need to get an expression for our ideal volume. Okay, so that's why we should rearrange this. So V ideal is equal to V real minus NB. Okay, so let's replace this expression in the ideal gas equation. So we have P ideal times V real minus NB is equal to nRT. Okay, so this is our van der Waals equation for now when we take into account the corresponding volume correction. Okay. Okay, so this is our equation so far. Okay, so let's look more closely at this term over here, our B term. Okay, so this tells us something about the excluded volume, right? So let's look more at the excluded volume. Okay, so the van der Waals equation of state, it imagines our gas molecules as hard, rigid spheres. So this is very similar to our consideration of molecular collisions. So we have our two molecules over here, so they're just colored in different ways in order to distinguish them. Okay, so if they just happen to collide with one another, okay, so they're just going to collide in the following way. Okay, so this molecule over here is going to just touch this other molecule here. Okay, so we could kind of draw out a circumference of closest approach. Okay, so this is the closest that this orange molecule here could approach this blue molecule over here. So if the center of this orange molecule here is going to be inside this region over here, it's not going to be possible. Okay, so imagine again that you're trying to push two billiard balls closer to one another. So this part over here, you start having their volumes overlapping, so this cannot happen. Okay, so the only place where the orange molecule is allowed to approach your blue molecule, this is going to be just along or outside this edge here, okay, this circumference. So the center of our molecule can only be along or outside this edge. Okay, so regardless where it is, okay, so it could be here, 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 or it could also be outside this edge. It's okay. Okay, but the thing is, the center cannot be inside. Okay, so we call this entire volume, actually, this entire sphere, the excluded volume per pair of molecules. Okay, so actually, when we're thinking about the excluded volume, it's not just equal to the volume of the gas molecules. It's actually equal to the volume of the gas molecules times 4. So let's see why that is. Okay, so let's look at a computation of this. So we have the radius r of our gas molecule, and then the radius of our excluded volume is going to be equal to 2r. So let's calculate the volume of a molecule. So this is going to be equal to 4/3 pi r cubed. Okay, so now let's look at the excluded volume per pair of molecules, or for two molecules. So excluded volume for two molecules is going to be equal to 4/3 pi. So our value of r is now 2r raised to 3. Okay, so this is equal to 4/3 pi r cubed times 8. Or in other words, 8 times the volume of a molecule. But keep in mind that this volume over here, this corresponds to the excluded volume for two molecules. Okay, so if we want to get the excluded volume per one molecule, we need to divide this by 2. Okay, so excluded volume per molecule, which is what B is, this is going to be equal to just 4 times the volume of the actual molecule. Okay, so this is what B is related to. Okay, so now let's look at our pressure correction. Okay, so the pressure correction is going to be due to the intermolecular forces of attraction of the gas molecules for one another. Okay, so let's consider what pressure is on a molecular basis. So according to the kinetic molecular theory, the pressure of a gas is due to the individual molecules colliding against the walls of the container. Okay, so it's related to the force that each of these molecules is going to have with the wall. Okay, so for an ideal gas, a molecule is going to hit the wall with a full force. Okay, so it's going to be based on its kinetic energy. However, if we have a real gas, consider the fact that this molecule over here, let's call this molecule A, is going to be interacting with these different molecules here. So our molecule A is going to be interacting with our different B molecules here. Okay, so the van der Waals equation of state accounts these interactions to be attractive in nature. Okay, so these B molecules are going to be pulling at this A molecule, so it's not going to be hitting this wall with full force. In fact, the velocity of A is going to be reduced to the extent of the intermolecular forces of attraction between this A molecule and the B molecules here. Therefore, we expect to have a lower pressure exerted by our real gases. Okay, so how can we account for this pressure correction? Okay, so recall again that our pressure, our real pressure, is expected to be less than the ideal pressure. So our correction is going to be subtracting from the ideal pressure. Okay, so overall, our real pressure is going to be equal to our ideal pressure minus some corrective term here, our P prime. Okay, so what is this P prime going to be? This P prime is going to be equivalent in some way to the attractive forces. Okay, so this is going to be proportional to, okay, the concentration of colliding molecules. Okay, so the number of moles of our colliding molecules. So based on the picture, those are our A molecules, and the concentration of our molecules pulling them inwards. Okay, so this over here, this is going to be due to the reduced collisions. Okay, and then this is going to be accounting for the reduced impulse on the sides of the container. Okay, so keep in mind, however, that we don't really need to distinguish them as A or B. Okay, so these are going to be the same gas molecules. So our corrective term, this is just going to be proportional to N over V squared. Okay, so the concentration of our gas molecules squared. Okay, so in order to get rid of this proportionality, we could introduce a proportionality constant. So let's call this A, N squared over V squared. Okay, so A, this is going to be a positive value. So this is going to be related to the intermolecular forces of attraction. Okay, so the greater the intermolecular force of attraction, the greater the A value tends to be. All right, so with this in mind now, let's introduce this P prime back over here. Okay, so P real is going to be equal to P ideal minus the attractive forces. Okay, so this is going to be equal to AN squared over V squared. Okay, so if we solve for P ideal, so P ideal, this is going to be equal to the real pressure exerted by the gas plus this corrective term here. Okay, so we'll be inputting this expression in our equation that we have. All right, so what is the equation that we have now, including the corrective, the volume correction? So we have P ideal times the real volume, so let's just call it V, minus NB is equal to nRT. Okay, so we have an expression for this. So P ideal, this was equal to the real pressure exerted by our gas plus A N squared over V squared. Okay, so if we write this down now, our van der Waals equation is going to be P plus AN squared over V squared times V minus NB is equal to nRT. Alright, so this over here, this expression here, this is our van der Waals equation of state. Okay, so again, we have these additional terms here, A and B, which are unique for each type of gas. Okay, so A and B, they're also empirically derived. But at least we have an interpretation as to what these terms actually mean. Okay, so A, this is related to the intermolecular forces of attraction, and B, this is related to the volume of the gas molecules. More specifically, this is related to the excluded volume, which is 4 times the volume of the gas molecules themselves. All right, so again, we have an equation of state with additional terms here that takes into account the variable behavior of our different substances. All right, so let's see how this can reduce to our ideal gas equation based on our limiting conditions. So let's write down our van der Waals equation of state. So it's pressure plus our corrective term here, an squared over v squared, times our volume minus NB is equal to nRT. Okay, so at our limiting conditions are pressure approaching 0, or it's actually easier to look at it in terms of our volume approaching infinity. We expect that the van der Waals equation of state is going to reduce to the ideal gas equation of state. Okay, so let's check out this term first. So when our volume is infinity, our volume is going to be much, much larger than our excluded volume. Therefore, this term over here, V minus NB, this just approaches a value of volume. Okay, so this part becomes negligible since our volume is super, super large. Okay, so let's look at our pressure term over here. Okay, so when volume is approaching infinity, let's look at the behavior of our corrective term over here. So an squared over v squared. So when this is infinity, okay, this whole term approaches 0. Okay, so when we look at this entire term over here, p plus an squared over v squared, okay, this just approaches 0, right, when volume approaches infinity. So this entire term here just reduces to pressure. So ultimately, when we put these two things together, we just have PV is equal to nRT, or the ideal gas law. Okay, so our van der Waals equation of state, it reduces to the ideal gas equation of state at the limiting conditions, namely when pressure approaches 0 or when the volume approaches infinity. Okay, so our van der Waals parameters A and B, again, they're empirically determined parameters, and they're also independent of temperature in contrast to our virial coefficients. Okay, so here's a nice table giving us the different values of A and B. Okay, so note again that A is dependent on the strength of our intermolecular force of attraction. So let's compare the A values for ammonia versus argon. Okay, so argon, this is a noble gas, so the intermolecular forces between argon molecules are just going to be van der Waals forces. Okay, so the intermolecular force of attraction for ammonia molecules are going to be hydrogen bonding, so they're much stronger. So we have a larger value of A compared to that of argon. Okay, so B is related to the size of our molecule. So let's compare, say, xenon versus helium. Okay, so xenon is lower in the periodic table, so it has a larger volume compared to helium, which is much higher. So as expected, we have a larger value for xenon compared to helium. Okay, so let's try this problem over here. So we'll be applying the van der Waals equation in order to calculate the pressure of a gas, and we'll also compare the results of this using the ideal gas law. All right, so let's write down the equation that we know. Okay, so the equation is P plus n squared A over V squared times V minus NB is equal to nRT. All right, so since we're solving for pressure, we'll be isolating the term P. Okay, so let's just rearrange this. Okay, so we'll have nRT over V minus NB minus n squared A over V squared. Okay, so it's now just a matter of plugging in all the values that we have. Okay, so we have P is equal to, so number of moles. So we're given 100 grams of carbon dioxide, and luckily we're also given the molecular weight of this. So this is just 100 grams times 1 mole of carbon dioxide divided by 44.01 grams times R, which is 0.08206 liters atmosphere per mole Kelvin, times temperature. So our temperature is 40 degrees Celsius. So let's convert this to Kelvin. So 40 plus 273.15. So this is 313.15 Kelvin. Okay, so let's write that down. divided by the volume, so that is 5 liters, minus again number of moles, so let's just have 100 grams divided by 44.01 grams per mole, times the value of B. Okay, so this is 0.0429 liters per mole. All right. Okay, so we have minus again number of moles, so we have 100 grams divided by 44.01 grams per mole squared times the value of A, so that is 3.610 liters squared times atmosphere over mole squared, all divided by volume squared, so that is 5.0 liters squared. Okay, so let's just check out the units of this. So the units of this, we have gram, gram canceled out. So we have mole squared here, so mole squared divided by mole squared times L squared times ATM. So mole squared cancels out here. Liter squared also cancels out. Okay, so know that the units of A is consistent in order to make sure that the term over here is always going to be pressure. Okay, so we have a pressure term here now. Okay, and then over here we have moles, moles cancels out, so grams, grams, moles. So we have liters. Okay, and then we have moles here as well. So moles here cancels out with moles. Liters cancels out with liters down here. Kelvin, Kelvin, and we're left with atmosphere minus atmosphere. Okay, so just always keep in mind that whenever you're doing an addition or a subtraction, you have to be subtracting values with the same units. Okay, so we're left with atmosphere, atmosphere, so that's all good. So we punch this in our calculator, we get 11.1 atmospheres. Okay, so let's just put it into 3 significant figures for now. All right. Okay, so let's try calculating this now with the ideal gas equation. Okay, so using the ideal gas equation, so the ideal gas equation is just PV is equal to nRT. So solving for pressure, this is straightforward. Okay, nRT over V, so let's just plug in the information. So we have 100 grams of carbon dioxide, so divide this by the molecular weight. And then we have R, and we have our temperature, divided by the volume, which is 5 liters. And if we punch this in, we get 11.7 atmospheres. Okay, so this is the ideal pressure. So let's compare that with the van der Waals pressure. So the one that we calculated was 11.1 atmospheres, right? So note that for the real gas equation of state, we have a lower predicted pressure. So this takes into account the decrease in pressure due to the intermolecular forces of attraction in our real gas molecules. Okay, so overall, the van der Waals equation of state gives us better predictions on the behavior of matter. Okay, so let's look at the van der Waals equation of state a little bit closer, and we'll realize something about the equation. Okay, so let's write down the van der Waals equation of state in terms of molar volume. Okay, so it's just a little bit easier to deal with the equation in terms of just molar volume. So we have P plus A over Vm squared, right, times Vm minus B is equal to RT. Okay, so it's just an equation that corresponds to 1 mole of matter, right? So what we're going to do here is that we're going to FOIL this. Okay, so we'll be multiplying out these terms here. Okay, so based on this, we get, okay, first term PVM, okay, outer terms PB, inner terms we have A over Vm, and then our last term minus AB over Vm squared. So this is all equal to RT, right? So let's get rid of this denominator in our term here. So let's multiply this whole thing by Vm squared, and we get PVM cubed minus PB VM squared plus A times VM minus AB is equal to RT VM squared. All right. Okay, so let's rearrange this and let's also divide the whole equation by P. Okay, so let's bring the RT times VM squared term inside here on the left side. So it's all going to be equal to 0. And let's also divide the whole thing by 1 over P. Okay, so if we do this, we get this expression, VM cubed minus PB, okay, plus RT over pressure times Vm squared plus A over P times Vm minus AB over P is equal to 0. Okay, so what do we have now? Let's box this equation here. This is still the van der Waals equation of state. It's just written out in another way. Okay, so this shows us that the van der Waals equation of state is actually a cubic equation. Okay, so what do we mean by that? A cubic equation. What's so significant about this? Okay, so if you recall from your math, okay, so first degree equations, that gives us lines. Second degree equation, that gives us parabolas. Cubic equations, what kind of curves does that give us? That gives us curves like this, right? Okay, so for each particular, like say that we want to get like a certain pressure here, okay, it's going to give us 3 roots, okay? So keep in mind here that our sort of x variable is our volume, okay? So if we have pressure plotted here and we have volume plotted here, okay, for every particular pressure, for certain cases, we're going to have 3 roots, okay? 3 possible values of V that will input a given pressure, okay? So let's consider the significance of this as well as the physical interpretation of these types of curves, okay? We'll also see that there's something really weird about this if we consider these curves. All right, so what is a PV curve, by the way? This is an isotherm at constant temperature. The PV curves, right? This is Boyle's law. For an ideal gas, we're expected to get like these nice curves here, right? But our van der Waals equation of state for certain conditions gives us these squiggly cubic curves. All right, so let's look at these different isotherms, okay? So for temperature 4, we have this nice curve over here. For temperature 3, we have this curve over here. We don't exactly have 3 roots yet, but at temperature 1 and temperature 2, this is when we have the case where we could have 3 roots for our van der Waals equation. Okay, so let's focus on one particular part on the temperatures over here at temperature 1 and 2. Okay, so recall again the basic principle. Okay, we know that if we have a gas or any sort of substance really, okay, so we have a system over here, we have a, let's say, a movable piston, okay, so that we can control the pressure. Okay, so we have a certain substance here. Okay, so what happens when we increase the pressure of our system? As in, we push down on this piston, what's going to happen to the volume? Okay, so increasing the pressure, what's going to happen to the volume? Okay, so intuitively, we know that if we compress something, matter, anything, whether it's a gas, liquid, or solid, most likely the volume is also going to decrease. Okay, so that makes physical sense, right? Okay, so you're exerting a force on the gases, so you're decreasing the space between the particles, right? So you expect that the volume is going to decrease. The same thing can actually apply for liquids and solids, but to a lesser extent, since liquids and solids are less compressible, but more or less you have this observation as expected. Okay, increase in pressure, you see a decrease in volume. Okay, so how should that be manifested in a curve? Okay, so This is like Boyle's law, right? So if you have a high pressure, you expect to have a low volume. If you have a low pressure, you expect to have a high volume. So this sort of trend is expected. Okay, so it doesn't have to be a perfect curve like this, but you do expect that there's going to be a negative slope. Okay, so there's an inverse relationship between pressure and volume. Okay, so what's the problem that we see in these curves over here? Okay, so for this curve, okay, so this is fine. You have like this negative first derivative here. What happens here? Okay, so at these points here, so to be more specific, you see these regions here that start to have something really weird, right? So what's the slope of this? This is a positive slope. So this part of the curve suggests that if you increase the pressure, okay, increasing pressure, you happen to increase the volume. What? That doesn't make any sense, right? Is that physically realizable? No, that's not physically realizable. That's why we call this particular region the physically unrealizable region. Okay, it just does not make any sense. Okay, so this is super weird. Okay, so actually you might be able to observe these sorts of states here. Like if you have a particular pressure here, you might have this corresponding volume, but it's not going to be stable at all. Okay, so what's being done here instead is that we need to make corrections and on the van der Waals isotherms, and we also need to investigate what exactly is going on here. Why do we see these weird sorts of shapes here? Okay, so what we need to do here, let's focus on isotherm T2, is that we add these sort of correction lines here. Okay, so instead of having this curve here, this upward, this slope here that is positive, we add a so-called Maxwell construction. Okay, so the Maxwell construction, that is the dotted line over here. Okay, so the real isotherm that's really observed for this particular case here is that you don't really see these lines here. You see this dotted line along here. So this is your stable state. Okay, so again, you might see some cases like this, but this is a not so stable state. Okay, so usually if you're in this particular state, you'll automatically go into this condition here. So what exactly happens at your Maxwell construction? Okay, so actually what's happening here in your Maxwell construction is that you see a phase change. Okay, phase change. Okay, so after all, note that only these squiggly lines here are observed for relatively low temperatures. Okay, so note again that temperature 4 is greater than temperature 3, is greater than temperature 2, is greater than temperature 1. Okay, so if you have isotherms at lower temperatures, you start to see these curves here, these cubic equations where you have 3 roots. Okay, so it's at these lower temperatures where you could start to observe some phase changes. Okay, so at these lower volumes here, okay, this is when you start having your liquid phase, and this is part over here, this is where you have your vapor phase, right? Okay, so we could also construct other Maxwell constructions for the other isotherms, so this also corresponds to another phase change. So if you are along this line here, in this condition over here, okay, so note that you have constant pressure. Okay, so you have a fixed pressure. Okay, so let's call this P2, and then let's call this P1. Okay, so you have a constant pressure, but note that your volume is changing. Okay, so recall again that we have a liquid here, right? And we have a vapor here, or a gas. Okay, so what's happening here is that if you're in the liquid phase, okay, so you're around here, right? And then you reach this particular pressure and temperature, okay, you start to increase your volume while retaining the same pressure. Okay, so this volume change that you observe here is your liquid slowly transforming itself into a vapor. Okay, so you have this equilibrium phase equilibrium. Okay, so you have your liquid in equilibrium with your vapor. Okay, so as you keep increasing your volume, okay, you're transforming some of your liquid into a gas. Okay, so this part over here, this corresponds to the molar volume of your liquid, and then this part over here, this corresponds to the molar volume of your gas. All right, so same thing goes over here. Okay, so again, since we have liquids on this part here, okay, so note that the slope of these curves are much more steep. Okay, so what does that mean exactly? Okay, so if we increase the pressure, okay, we're increasing the pressure, we're going up on this y-axis over here. Note that there's not much change in the volume, okay, because liquids are less compressible. However, if you're in the vapor phase now, note that the slope is not that steep. Okay, so if you're increasing the pressure, okay, you see a larger change in volume because gases are more compressible than your liquids. Okay, so overall we have this summary of our isotherms now. Okay, so note here we have our Maxwell constructions already. Okay, so within this blue shaded region, so keep in mind we have a bunch of other isotherms that are not drawn here. We have liquid to gas equilibrium. We have a phase change occurring in these conditions. Okay, so we have our liquid phase here, we have our gas phase. Okay, so note that there's going to be a particular isotherm in which we see the peak. Okay, so this is called your critical point. Okay, so note that you no longer see any liquid to gas phase equilibrium above this temperature. Okay, so if you recall what the critical point is, okay, so let's look at another phase diagram that you are probably familiar with. Okay, so this is a pressure temperature phase diagram, so you could see the different temperatures and pressures at which different phases are going to exist. So this particular plot here has a correspondence to this plot here. Okay, so we have our liquid phase. Okay, so this might correspond to this region over here. So we have an isotherm T1. We have a phase change going on over here. So this temperature here might be T1. This temperature here might be T2. And then once you hit T3, that is when we are at the critical point. So beyond the critical point, we now have a so-called supercritical fluid. Okay, so that's why we no longer have any Maxwell constructions. Okay, so this is the maximum temperature where you'll see any liquid to vapor phase equilibrium. Okay, in fact, beyond this point, we have the supercritical fluid. Okay, so if you recall what you know about the supercritical fluid, for supercritical fluids, you can no longer distinguish these between a liquid and a gas. Okay, so what exactly is a supercritical fluid? So let's say that we are below the critical temperature at first. Okay, so at this temperature, this is a lower temperature, we could distinguish between the liquid and the gas phase. Okay, so the liquid is characterized by a very large density compared to the density of a gas. Okay, however, if you start increasing the temperature, the density of your liquid starts becoming less and less, and the density of your gas also starts to become more dense. There comes a point where the properties of your liquid and your gas become the same so that they become indistinguishable. So the obvious property for this is density. Okay, so note at which conditions a supercritical fluid is going to occur in. Okay, so our critical point occurs at a relatively high pressure and a high temperature. Okay, so at high pressures, okay, the density of our gas is going to be very large. Okay, so the density of the gas is going to be so large to the extent that it looks like a liquid. However, the critical point also occurs at relatively high temperatures. So what does this mean? High temperatures means that your kinetic energy of your molecules also tends to be quite high. Okay, so the kinetic energy of your particles is high enough that it doesn't really behave like a liquid exactly. Okay, so while the density of the supercritical fluid is also high, it also has a very high kinetic energy. So it behaves kind of like a gas, it behaves kind of like a liquid. So we just call it a supercritical fluid since it tends to have behaviors of a gas and a liquid. Okay, so the van der Waals equation of state gives us a better description on the behavior of matter. Okay, so it improves upon the ideal gas equation of state by considering the intermolecular forces of attraction between our molecules, as well as the molecular volume of our substance. Right, so by analyzing these pressure volume curves, we're also able to see how the van der Waals equation predicts a critical point. Okay, so while we also saw that the van der Waals equation of state is a cubic equation that results in really strange predictions, okay, so we just added some additional corrections to our van der Waals curves. And from there, we were able to see that we have phase changes occurring in these particular conditions. Okay, so we could see that our van der Waals equation of state can actually apply for the liquid phase as well as for the gas phase. All right. However, we always have to keep in mind that the van der Waals equation of state does have its limitations. So there are some conditions in which it does not give very accurate predictions on the parameters of our system. So for one, when we were talking about the volume of our gas molecules, we treated the molecules as hard rigid spheres, which is not always the case. And we also, in terms of our intermolecular force of attraction, we just considered attractive forces. Okay, so there are other equations of state that make additional corrections to this and give better predictions. Okay, but overall, the van der Waals equation of state is a nice place to start studying different equations of state. Okay, so overall, we'll just end here for our discussion for our real gases. Okay, so if you're interested in studying more about different real gas equations of state, okay, you could refer to many other physical chemistry textbooks.